dear friends, we were discussing about static stability, and we realized and we understood when we define static stability, we are very clear that it is to do with initial tendency of that system. If it has initial tendency to come back to the equilibrium, then the body or the system is in static stability. Okay? And we try to understand this through a diagram. If this is the spring and this is a mass, so this is the equilibrium, and equilibrium means all the net forces and moments are zero. And once we want to understand static stability, what we say, we disturb this, we stretch this mass and release it, and we know that the moment I stretch it, there is a force kx proportional to the displacement. It tries to take it back to the equilibrium. It may overshoot, it may oscillate, that's a different issue. For static stability, those things are not important. For static stability, it's only important that it should have initial tendency to go towards the equilibrium. That is static stability. Now, for this mass spring system, who is providing these static stability characteristics? It is through the spring. The moment I stretch the spring, there is an opposing force which tries to take it back to the equilibrium. Now, let us come back to the aircraft. If I say, for aircraft, for time being, if we concentrate on the angular stability, that is, suppose the airplane is going like this, and if there is a disturbance which tries to take the attitude up, we have to check it will be statically stable if it has initial tendency to come back to the same equilibrium, okay, or to the equilibrium, that initial tendency. That means for a mass spring system, it has a spring which does all this work. But for an aircraft, what is that agency who will ensure that the moment I am deviating from the equilibrium, there will be a restoring moment which will try to take back it to the equilibrium. That is, if it is going like this, if it is disturbed and its attitude has increased, then the aircraft should have a mechanism which should try to give a nose down moment to ensure that it has static stability. Is it clear? Now the question is, for a mass spring system, there are physical systems like spring, mass, and spring is giving what force or forces. However, for an aircraft, all these forces are being generated through interaction between body and the medium, which is air in this case, right? For example, you know, aircraft has major component as wings, as horizontal tail, vertical tail. So whatever disturbance it experiences, if at all any restoring moment has to be generated, it has to come from the interaction of the horizontal tail, wing, fuselage. From their interaction, it should generate a nose down moment. As long as it generates nose down moment for a positive disturbance, angular disturbance, angle of attack disturbance, we will say it has static stability. Now we will try to understand where from it will generate a restoring moment almost analogous to a spring. Okay, let us see. We all are aware of aerofoil. Let's, for simplicity, assume that this is a symmetric aerofoil, and also we know there is a point called Aerodynamic Center. Aerodynamic Center. And what is the definition of aerodynamic center? It is a fictitious point, mostly for low speed and moderately thickness to chord ratio aerofoil. This point is at c/4, that is, its location is c/4, and we call it quarter chord point, where we are now very clear what is a chord. And what is the technical definition of this aerodynamic center? It is that point in the aerofoil about which the pitching moment is independent of angle of attack. Is it clear? I mean, even if I change angle of attack, the pitching moment about that point will be 0. Right? So it is very convenient to represent all the forces and moment acting at c/4. So you will find that for an aerofoil, I will represent like this CL, CD, and in general there will be a CM. Okay. Now let us try to understand how such configuration can generate a restoring moment to ensure it has static stability. That is the question we are addressing. It is important to understand that in free flight, if there is any disturbance on the body, it will try to rotate about an axis passing through center of gravity. So we will like to see whatever moment is being generated, all the rotation about an axis passing through center of gravity. So what do? We say, suppose this is the aerofoil, and I can now imagine that this aerofoil is a cross-sectional contour of a wing. We are very clear, we have already discussed, the aerofoil is a two-dimensional concept where the flow is supposed to follow the contour. There are no lateral flows, but for a wing there will be lateral flows. But the wing contour is decided by the aerofoil. Also we know lifting characteristic of the wing also depends upon what type of aerofoil you have chosen, right? But what we are trying to focus is on stability, mostly static stability at this point. So this is aerodynamic center. Let us say this wing I want to fly. Okay, it has enough area. Now there are two positions are possible. One is, let's say, center of gravity of the wing is ahead of aerodynamic center. Correct? If this is the situation, let's see what happens. Let's say this gentleman is flying at alpha equal to alpha star, and that is the equilibrium. And because of some disturbance, delta alpha, the wing is going to respond. We are looking for its initial tendency. If there is a delta alpha disturbance, then a delta CL, I say lift coefficient or a lift, if I multiply it with dynamic pressure, will be generated, and that can be represented effectively at aerodynamic center. We have agreed on this point. Now if this is true, then what this delta CL will do? This will generate a moment, I say delta Cm, about Cg, which will be nose down. So if there is a positive disturbance of delta alpha, this wing has a tendency to put the wing down to make this to 0 or to come back to the alpha star. So we say it has initial tendency and to come back to equilibrium. So we said if aerodynamic center is behind center of gravity, then it possesses static stability. Is it clear? To be more elaborate, suppose the aircraft is trimmed at alpha 2 degree, I call it alpha star, and there is a delta alpha, let's say 0.5 degree. If this is statically stable, then what will happen? Because of delta alpha, now the angle of attack became 2 plus 0.5, 2.5 degree. But if it is statically stable, the airplane will have an initial tendency or produce a nose down moment, so that finally this gets cancelled, or there is a tendency to cancel it, right? I will not use the word finally, because finally once I say, I am implicitly talking about time, which static stability has nothing to do with time, that is dynamic stability. So correct statement will be, the moment there is a change in angle of attack from 2 plus 0.5, that is 2.5 degree, the airplane will generate a nose down moment to ensure that it has an initial tendency to come back to alpha star 2 degree. And this is possible for a wing alone configuration only when aerodynamic center is behind center of gravity. So you could see that the moment delta Cm, which is proportional to the angle, is equivalent to the spring force Kx. There also the spring force was proportional to the displacement. That was linear displacement, here is angular displacement. Here, both are in opposing nature. So that is how static stability is assured. You can immediately see that if this is the aerodynamic center and if CG is behind aerodynamic center, or I say aerodynamic center is ahead of center of gravity, then what happens? If there is a disturbance delta alpha, there will be a force here. Let's say in non-dimensional form I call delta CL. This will give nose up moment, right? So this will actually take this way, nose up. So further this angle will increase. So such configuration doesn't have any initial tendency to come back to the equilibrium. So we said this is statically unstable. So what is our learning? If we want to make a wing alone configuration statically stable, I must ensure that aerodynamic center of the wing should be behind center of gravity of the wing, right? And we also realize that the production of moment, which is proportional to the angular displacement, can be thought to be analogous to the production of force because of linear displacement for a spring mass case. So I can always say this separation between aerodynamic center and center of gravity will have some relationship or some similarity with the stiffness of the system. Like for mass spring system, the spring constant K has some influence on the stiffness of the system. Okay, so this needs to be understood correctly before you again revisit my lecture on static stability. Okay, now if you recall, the aircraft has mainly this is the horizontal, mainly those stabilizer component and lifting component. What is the lifting component? Primary lifting component is the wing. That is, wing has a primary role to generate lift, and this part is the stabilizer, and its role is, this is typically horizontal stabilizer, its role is to give stability to the airplane, right? So now if I draw a configuration like this, and let's say CG of the airplane is here, and aerodynamic center of the wing is here, and aerodynamic center of the tail is here. So by seeing this diagram, can we simply tell, or can we not answer a question by seeing this description and neglecting the fuselage effect? So let's say fuselage effect we are neglecting. With this assumption that we are neglecting fuselage effect, by seeing the location of aerodynamic center vis-a-vis CG of the airplane. This is CG of the airplane. Please understand, when I am drawing here, this notation is, this is CG of the airplane. Earlier, since it was only wing, so I was talking about CG of the wing. But this is whole airplane. This is the CG of the airplane. Why CG of the airplane? Because airplane will rotate in free space through about an axis which passes through CG of the aircraft, right? Once I have represented the location of aerodynamic center of wing as well as tail vis-a-vis the CG of the airplane, I can easily comment that this configuration will necessarily be statically stable. I am assuming there are no fuselage effect or neglecting fuselage effect. Why I know? Because aerodynamic center of the wing is behind CG of the airplane, so this will be stabilizing. Anyway, aerodynamic center of the tail is behind CG of the airplane, so this will be stabilizing. So this aircraft has to be statically stable. There is no issue. Now think of a different case. Think of a case where CG of the airplane is behind aerodynamic center of the wing. However, aerodynamic center of the tail is behind CG of the airplane. Can I directly say this aircraft will necessarily be statically stable? I am assuming that fuselage effect is neglected. Can I directly tell? Let us investigate. As far as wing is concerned, since aerodynamic center of the wing is ahead of CG, it is giving destabilizing. Okay. So this is not giving stabilizing contribution, because I know for stabilizing contribution, aerodynamic center has to be behind center of gravity. But for tail, it is of course behind, so it's stabilizing. So whether the aircraft will have adequate static stability or not, or to be more straight, whether the aircraft will be statically stable or not, will be decided by the actual contribution of wing, which is destabilizing, and actual contribution of tail, which is stabilizing, and they will try to nullify each other, and whosoever wins, that will decide is statically stable or not. If the contribution of tail is more than the contribution of wing, then I will say statically stable. For example, the restoring moment, which is primary reason for static stability in this case. So the restoring moment generated by the horizontal tail, if it is more than the disturbing moment or destabilizing moment generated by the wing, then only this airplane will be statically stable. And the restoring moment is decided by what? You could see not only the horizontal tail, whatever lift is coming or area, but also the distance between horizontal tail, aerodynamic center and the CG, because it is a moment. Okay. So soon you will understand that when you talk about static stability, we talk about the area, we talk about the momentum, and we define some term called tail volume ratio. So this is just to warm you up. This concept should be clear to you. Also, please understand, suppose this is an airplane. So this is CG of the aircraft, and let us see AC of wing, and of course this is AC of tail. Okay. Let's say this is the configuration. Again, I am assuming fuselage contribution is neglected. If I see this, I could easily check, yes, AC of the wing is behind CG of the aircraft, so this will give stabilizing contribution. Anyway, AC of the tail is behind the CG of the aircraft, this also will give stabilizing contribution. So it is necessarily having static stability. But now, suppose I add some surface here. Okay, which are typically called canard. Then what will happen? The static stability will increase or decrease. How do I see it as a designer? Okay, I know that the moment it is like this, the aerodynamic center of this canard is ahead of CG of the aircraft. So what it will do? It will give, again, destabilizing. Clear? We know that aerodynamic center is ahead of center of gravity of the aircraft, so it will destabilizing. So whatever static stability it had without this canard, now the moment I put canard, its static stability will reduce. And if it is not properly designed, it may become unstable also, right? Statically unstable also. So this is what the scenario, and what is the gross learning for a designer? That any lifting surface, please note this importantly, any lifting surface which are located behind the center of gravity of the airplane will generate stabilizing effect. Any lifting surface which are located ahead of center of gravity will generate destabilizing contribution. If you understand this, then major part of static stability is understood. It doesn't require more than a knowledge of class 11th or 12th. You have to know how to find out the moments. Is it clear? Okay. Let us take another example before you go through those lectures. Let's say a very simple case. Let us say this is a hinge point. Let us say I have put a horizontal surface like this, and I have kept this in a wind tunnel. You are all aware of this nomenclature. You know what is a wind tunnel? Okay, when I say hinge point means, so this is a horizontal tail, so it is located like this and it can rotate about this point in a pitch plane. And we say, remember, we call it longitudinal motion, right? But it cannot go forward or backward. So only 1 degree moves like this. So now, if this is the case, can we talk about whether this is statically stable or not? What is the way to think? You first identify what are the lifting surface. Is that only one lifting surface, that is this one. And you know the aerodynamic center will be C/4 of this. So let's say this is the aerodynamic center. And now what is the check? Since it is rotating about hinge point, so it is like the center of gravity for a free space. But in free space also it rotates about center of gravity, axis passing through center of gravity, right? So this is the hinge point. So now this, you could see aerodynamic center is behind the hinge point. So this will give necessarily static stability, okay, as per our understanding. But mechanics wise, let us check how it happens, okay. Suppose this is a system, and suppose I have given, let me draw it till, once you understand this is the tail, so I am drawing the cross section. Okay, assume the tail is something like this, okay? So now I want to check whether it has static stability or not. Though we understand, we have become expert, we know the aerodynamic center is behind the CG or the hinge point in this case, so it will definitely contribute towards static stability, right? Let us see by mechanics wise what happens. Let's introduce some disturbance of 2 degrees. Remember, this is the equilibrium, okay? Equilibrium is at, let's say, alpha equal to 0 degree. Now I introduce 2 degree disturbance. So equilibrium is at alpha equal to 0. I introduce a disturbance of 2 degree. So what this 2 degree will do? At C/4, it will generate a lift. I am representing by CL, this coefficient, and we know very well if I multiply with the local dynamic pressure and area, I will get the total lift. Here there is one assumption. Generally, or as per definition, the lift should be perpendicular to the velocity vector, but since alpha is small, 2 degree, we are assuming it to be straight. That's all, right? What the CL will do? The CL will immediately generate a moment about hinge point, so which will also depend upon what is the length LT. So the moment it generates a nose down moment, meaning thereby what? It will try to nullify this 2 degree, so it has an initial tendency to make it, or to ensure it comes back to alpha equal to 0, which is the equilibrium. So you say, yes, indeed, it has static stability. Is it clear? But there is a catch. Please understand what happens. Suppose I have fired a rocket which has thrust T and which is statically stable. this is the CG, and this is the aerodynamic center or center of pressure for this. It's statically stable, and it was having alpha equal to, let's say, 0. Now, because of disturbance of 2 degree, what will happen? Because it is statically stable, it has initial tendency to ensure that this 2 degree becomes 0, so that the equilibrium alpha equals 0 is achieved. So it gives a nose down moment. The moment it gives a nose down moment, the rocket, initially rocket turns like this, but the thrust is on already, right? So it will have a serious effect on the range of the rocket, because which is supposed to go like this, it is now turned like this, and thrust is on, so it will, the elevation angle will change, so the range of the rocket will change. That is why it is important when you talk about stability, how much stability. So as far as static stability is concerned, it talks only about initial tendency, but it has larger influence on its sensitivity or in performance, in dispersion vis-a-vis wind. So it is very, very important. We should also clearly know how much static stability we want. And our lecture will address this question. As I told you, these are all warm-up for this course. My role is to orient you towards stability, to understand, and to have a love and hate relationship with static stability. You love it, don't love it too much. Don't hate it, okay? So how much I should love, how much I should hate, that will be decided by what do you require and how much you understand. Okay, clear? So that's why I always say static stability and control has a very tacit relationship. One has to respect it. If you don't respect, that whole relationship can break and you may lead to a disaster. Okay? Thank you.